It's only the third one ever. There's, 1.5 million known asteroids, and there's about 35,000 near-Earth objects.
The object, now officially named 3I Atlas.
When 3I, Atlas, only the third confirmed interstellar object in history, streaked into the solar system in July 2025, telescopes worldwide turned to study it. Yet, behind the scenes, another network of watchers already stood ready, the US Space Force. The newest branch of the American military has built the most comprehensive surveillance system ever deployed in orbit. Now, there are rumors that Space Force intercepted a transmission linked to 3I ATLAS. What is the truth? Today, we'll unveil everything. What did the ATLAS survey find? On the 1st of July 2025, the Asteroid Terrestrial Impact Last Alert System, better known as the ATLAS survey, detected an object moving through the sky that did not behave like anything belonging to our solar system. Operating under the University of Hawaii, the survey runs a network of telescopes designed to identify near-Earth objects that could pose impact risks. That morning, the telescope stationed in Chile picked up the faint trail of a comet-like body.
It was detected by a University of Hawaii-operated telescope in Chile.
At first, it seemed like a routine detection, but as orbital calculations were refined over the following days, it became clear that the object was traveling along a hyperbolic path, one that would bring it through the inner solar system before sending it back out into the interstellar void. This was the third time in history that astronomers confirmed the arrival of an interstellar visitor. Initially labeled C2025N1, the object was later reclassified as 3I Atlas, joining the exclusive company of 1I Oumuamua, found in 2017, and 2I Borisov, observed in 2019. 3I Atlas came from beyond the solar system, and this was no small matter. Most comets orbit the Sun in predictable ellipses or parabolas, their icy nuclei looping around before retreating to the cold outer reaches of the Oort cloud. In contrast, 3I-ATLAS has an orbital eccentricity greater than 1. This means that it is not bound to the Sun's gravity. Its velocity is roughly 58 kilometers per second relative to the Sun. Such speed far exceeds that of typical solar system comets, leaving no doubt that this object originated in the depths of interstellar space. Calculations project that its closest approach to the Sun, its perihelion, will occur in early 2026, at a distance still beyond the orbit of Mars. After that brief encounter, it will continue its outward journey and never return. Unlike 1I Oumuamua, whose asteroid-like body showed no coma or tail, or 2I Borisov, which behaved much like a conventional comet, 3I Atlas presents its own distinct characteristics. Observations revealed a bright coma and a developing tail, both signatures of volatile materials vaporizing under the Sun's heat. This activity provides astronomers with valuable opportunities to study its chemical makeup. The nucleus itself is believed to be no larger than 5 to 6 kilometers in diameter, a modest size compared to some of the giant comets catalogued within our system, but it is large enough to sustain significant outgassing. Once the Chilean telescope logged 3I-ATLAS, other observatories quickly joined in. The Vera C. Rubin Observatory in northern Chile, which had been preparing for full operations, contributed follow-up observations that helped refine the comet's orbit. Space-based instruments also entered the picture. The Hubble Space Telescope provided high-resolution imaging, while the James Webb Space Telescope trained its infrared capabilities on the object, gathering spectral data that revealed the presence of carbon dioxide and possibly water ice. Brightness levels of 3I Atlas have made it accessible to a wide range of instruments. Although not visible to the naked eye, it can be tracked with mid-sized telescopes, allowing both professional astronomers and some advanced amateur observers to contribute to the data pool. The comet's coma, illuminated by solar radiation, provides the kind of detail that was absent in the study of Oumuamua. For example, while Oumuamua left scientists debating whether it was a shard of rock, an unusually thin disk, or even an exotic form of ice, 3I-ATLAS immediately showed the typical behavior of a comet under solar influence. This makes it an excellent test case for comparing interstellar bodies against the wealth of data already collected from local comets. The discovery of 3I ATLAS also adds to our growing statistical understanding of how frequently interstellar objects enter the solar system.
3I Atlas was discovered on July 1st by the NASA-funded Discovery using their telescope at Rio Hurtado in Chile.
For centuries, such arrivals were purely hypothetical, but now, within less than a decade, 3 have been observed. The International Astronomical Union's Minor Planets Center confirmed the object's interstellar status once sufficient data had been gathered. NASA's Jet Propulsion Laboratory produced precise orbital solutions, ensuring accurate projections of its path through the solar system. The National Science Foundation and the Department of Energy, partners in the operation of the Rubin Observatory, facilitated critical follow-up campaigns. Observational campaigns. The object's interstellar origin meant that astronomers had only a limited window of time to gather as much data as possible before the comet faded back into the darkness of space. From the outset, observatories across the world and in orbit coordinated their resources, creating an unprecedented multi-instrument effort to capture the object's orbital, physical, and chemical properties. The campaign reflects how modern astronomy functions, an interconnected global network where ground-based and space-based observatories contribute complementary datasets, all coordinated through the clearinghouse of the International Astronomical Union's Minor Planets Center. The initial detection was made by the ATLAS survey, a system specifically designed to find small objects that might pose threats to Earth. Operated by the University of Hawaii's Institute for Astronomy and funded by NASA's Planetary Defense Coordination Office, ATLAS consists of 4 telescopes, 2 located in Hawaii, 1 in South Africa, and 1 in Chile. It was the Chilean telescope, situated at El Saus Observatory in the Rio Hurtado Valley, that first logged the comet. Within hours, the detection was relayed to the MPC in Cambridge, Massachusetts, which is the international hub for cataloguing small bodies. Among the most significant facilities brought into the effort was the Vera C. Rubin Observatory, located on Cerro Pachon in northern Chile. Although still in its commissioning phase in 2025, Rubin's 8.4-meter Simony Survey Telescope and its 3.2 gigapixel Legacy Survey of Space and Time, or LSST, camera were already capable of contributing high-precision imaging data. Rubin is expected to revolutionize time-domain astronomy when it enters full operation, and its early observations of 3I-ATLAS offered a preview of its potential. The facility's wide-field imaging allowed astronomers to map the comet's brightness variations and track its coma expansion, providing data points crucial for refining models of its activity as it approached perihelion. Other ground-based observatories soon joined in. The European Southern Observatory's Very Large Telescope at Paranal in Chile provided high-resolution spectroscopy, enabling researchers to identify the gases released from the comet's surface. Observatories in the Canary Islands, Hawaii's Mauna Kea, and even medium-sized telescopes operated by university consortia added to the data stream. Space-based instruments offered capabilities unavailable from the ground, particularly in wavelengths blocked by Earth's atmosphere. The Hubble Space Telescope, though more than 3 decades old, remains one of the sharpest optical imagers available.
It has this direct window to the rest of the universe. There's nothing in between the rest of the universe and Hubble.
Soon after 3I, Atlas was confirmed. Astronomers secured directors' discretionary time to point Hubble at the comet. Its images resolved the structure of the coma and tail with fine detail, and its spectrographs detected emission lines consistent with carbon dioxide and carbon monoxide, volatile compounds that drive cometary activity. Because Hubble observes above Earth's atmosphere, it could also track the faint outer regions of the coma without the distortion caused by atmospheric scattering. Even more valuable were the observations made by the James Webb Space Telescope. Launched in December 2021 and stationed at the Earth-Sun L2 point, JWST is optimized for infrared astronomy. Its instruments, including the near-infrared spectrograph and mid-infrared instrument, are capable of identifying the molecular fingerprints of volatile ices and dust grains. JWST observations of 3I Atlas in late 2025 revealed absorption and emission features that confirmed the presence of carbon-bearing volatiles and suggested possible traces of water ice. These results allowed astronomers to directly compare the chemistry of an interstellar comet with that of solar system comets. For the first time, scientists could test whether the building blocks of planets and comets in distant star systems match the materials that formed our own. Coordinating such a vast campaign required institutional oversight, and that role fell primarily to the Minor Planets Center, the MPC, operated by the Smithsonian Astrophysical Observatory under the auspices of the IAU, is the global authority for cataloguing small bodies in the solar system. As positional data for 3I, Atlas arrived from telescopes worldwide. The MPC refined the comet's ephemeris and distributed updated orbital solutions to the community. This ensured that observatories could schedule observations at the right times and positions. NASA's Jet Propulsion Laboratory in Pasadena, California, published refined orbital elements through its Horizons system, allowing both professionals and amateurs to accurately track the comet. Teams of astronomers in Europe, North America, Asia, and South America divided tasks, with some focusing on orbital dynamics, others on compositional analysis, and still others on photometry. Preliminary results have already appeared on RxIV, the open-access preprint server. Then there are peer-reviewed publications. Journals such as Nature Astronomy, the Astrophysical Journal Letters, and Astronomy and Astrophysics all carry early results. The timing of the discovery also coincided with advances in global sky surveys. Alongside Rubin, facilities such as the Pan-STARRS telescopes in Hawaii and the Zwicky Transient Facility at Palomar Observatory in California provided broad sky monitoring, ensuring that sudden changes in brightness or activity could be detected and investigated. These facilities, though not as powerful as Rubin or Webb, contributed to the comprehensive picture of the comet's behavior, especially its dust production rates and rotational characteristics. The fact that so many observatories, from massive 8 to 10 meter class telescopes to smaller robotic survey instruments, were brought together goes to show just how serious the scientific community is about these interstellar visitors. Continuous monitoring is needed so that scientists can build a complete profile of its behavior under solar heating. Observations will continue until the comet fades beyond the reach of current instruments, after which the accumulated data will serve as a permanent record for comparative studies. By then, thousands of images, spectra, and positional measurements will have been logged. But since this is not the first interstellar visitor, one can't help but compare. Comparison with previous interstellar objects. When astronomers speak of interstellar visitors, the list remains short, but enormously important. In just 8 years, humanity has gone from never having observed such an object to now having 3 confirmed cases. The first, 1I Oumuamua, was spotted on October the 19th, 2017, by the Pan-STARRS 1 telescope in Hawaii. Its trajectory, an unmistakable hyperbolic path, proved that it originated outside the solar system. Yet what puzzled scientists was its lack of a coma or tail.
An object that has come from beyond our solar system.
Traits usually associated with comets. Photometric analysis revealed wild fluctuations in brightness, suggesting a highly elongated, possibly flattened body, perhaps cigar or pancake-shaped. This led to debates about whether Oumuamua was an asteroid-like fragment, a nitrogen ice shard, or even an artificial object. Harvard astronomer Avi Loeb famously put forward the hypothesis that it could be a fragment of alien technology, perhaps a solar sail.
It moved too fast to be bound to the sun. Very first object that we have found coming to us from interstellar space, from other.
The second confirmed interstellar traveler, 2I Borisov, provided far clearer data when discovered on August the 30th, 2019, by amateur astronomer Gennady Borisov at his personal observatory in Crimea. Unlike Oumuamua, Borisov displayed classic cometary activity from the beginning, with a bright coma and a long dust tail easily observable by ground-based telescopes. It passed through perihelion in December 2019, giving scientists months of observing time. Spectroscopic studies conducted by the European Southern Observatory's Very Large Telescope in Chile and NASA's Hubble Space Telescope showed that Borisov's chemical composition was strikingly similar to solar system comets, containing water, carbon monoxide, and dust grains. One paper, published in Nature Astronomy in 2021, even reported that Borisov contained unusually pure carbon monoxide ice, suggesting it had formed in the extremely cold outer regions of its home star system. The fact that Borisov looked so similar to comets found in our own planetary neighborhood reinforced the idea that the processes of planet and comet formation are universal across the galaxy. Then came the third visitor. Unlike its predecessors, Atlas is both brighter and larger, with its nucleus estimated to be less than 5 to 6 kilometers in diameter, making it easier to observe. Its speed, measured at roughly 58 kilometers per second relative to the Sun, ensures that it will traverse the inner solar system rapidly, with its perihelion in early 2026, passing beyond the orbit of Mars before heading back outward. Oumuamua was only about 100 meters long, faint, and fast-moving, which limited observations to a matter of weeks. Borisov, at about 1 kilometer across, provided months of data, but was still relatively small. Atlas, potentially 5 times larger than Borisov, is bright enough to be tracked for over a year with professional instruments. This extended timeline allows astronomers to analyze its coma and tail, track changes as it approaches and recedes from the Sun, and measure isotopic ratios in its gases that could reveal the conditions of its formation system. The appearance of ATLAS proves that interstellar objects are not exceedingly rare. But what does that mean for us, defense-wise? The Space Force connection. Since its formal stand-up in December 2019 and operational full structure by 2022, the US Space Force has placed Space Domain Awareness, or SDA, at the core of its mission. SDA is defined broadly as detecting, characterizing, tracking, and predicting objects and activities in space that might impact US or Allied interests. Space Delta II, or DL2, is the operational unit charged with executing that mission. Based at Peterson Space Force Base in Colorado, DEL2 operates globally dispersed sensor systems, fuses data from US and Allied sources, and maintains what is commonly called the Space Surveillance Network, or Space Object Catalog. DEL2 has been tracking on the order of 45,000 man-made space objects, including active satellites, space debris, and analyst objects. The latter require special attention. A major tool in the Space Force surveillance arsenal is the Space Fence radar system.
Satellites and debris litter the skies, posing an imminent threat to America's space assets.
Operational since 2020, Space Fence is located on Kwajalein Atoll in the Republic of the Marshall Islands and uses advanced S-band digital phased array radar technology. Its sensitivity allows detection of objects as small as a marble, roughly 4 inches or 10 centimeters, in low Earth orbit, and its rapid update cadence enables real-time tracking of satellite maneuvers, debris fragmentation, and closely spaced objects. Before Space Fence, the Space Surveillance Network catalogued roughly 20,000 objects. After its deployment, analysts expect that number to climb substantially. Complementing ground-based radar, the Space Force maintains space-based surveillance assets. The Space-Based Space Surveillance, or SBSS, satellite, launched in September 2010, carries visible sensors on an agile 2-axis gimbal, allowing continuous observations of Earth orbit. From its roughly 390-mile Sun-synchronous orbit, SBSS can collect metric and identification data on resident space objects. The data are routed through the Space Force Satellite Control Network and fed into the Delta IX Space Operations Squadron based at Schriever Space Force Base. Expansion of deep space radar capability is underway. The Deep Space Advanced Radar Capability, or DARC, is a multilateral project involving the US, Australia, and the UK, with Northrop Grumman as a key contractor. DARC aims to improve detection, tracking, and surveillance of objects in geosynchronous and higher orbits, complementing Space Fence's low Earth orbit sensitivity. At the institutional level, the Space Force has also contracted to upgrade its Space Domain Awareness Command and Control architecture through programs like MOSAIC, which is short for Maintenance of Space Situational Awareness Integrated Capabilities. The goal is faster fusion and dissemination of sensor data across military, intelligence, commercial, and allied networks. Another Space Force asset relevant to broad space awareness is the 15th Space Surveillance Squadron, located at the Maui Space Surveillance Complex, or MSSC, on the summit of Haleakala, Hawaii.
Military officials are proposing to build more telescopes on Maui's Haleakala.
MSSC hosts large optical tracking telescopes and the ground-based Electro-Optical Deep Space Surveillance, or GEODSS systems, which are used to track deep space objects and provide imagery and orbital refinement. But what does all this have to do with an interstellar comet like 3IATLAS? Well, the Space Force's programs are focused on Earth-orbiting objects, satellites, debris, and near-Earth objects that might pose collision or threat risks. Space Fence is optimized for tracking objects in low to medium Earth orbit, and the SBSS satellite watches resident space objects relatively close to Earth. 3I Atlas, by contrast, traveled on a hyperbolic trajectory through the inner solar system, coming from interstellar space and destined to exit again, never to orbit Earth or settle into a geocentric orbit. However, there are a few realistic ways the Space Force and astronomical campaigns could intersect when unusually fast or unanticipated objects enter the inner solar system. First, space domain awareness networks are increasingly being designed with anomaly detection in mind. In 2025 remarks, the Chief of Space Operations emphasized that one of the top priorities for the Space Force is space domain awareness, paired with resilient satellite architecture and counter-space capabilities. If an object like 3IATLAS exhibited unexpected behavior, say unplanned maneuvers, fragmentation near Earth, or potential signals, it could, in principle, trigger alerts in SDA systems. Second, because the Space Force integrates data from ground and space-based sensors, including radars and optical systems, it is possible that unusual detections, even from deep space, could be cross-checked or logged if they impinge upon or transit near Earth orbit. If, for instance, parts of an interstellar object were to transit close to geosynchronous orbit, or debris from it were to enter Earth's vicinity, they could become part of the Space Surveillance Network cataloging process. Third, the trend toward building deep space radar systems, like DARC, suggests the Space Force is investing in the capability to detect more distant or faster-moving objects in the solar system more broadly, not just those bound to Earth orbit. While DARC is not explicitly framed as a comet hunter, its development shows that space surveillance capabilities are being extended further out. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.